Okay, it is 2 o'clock. Welcome everyone. Welcome to today's webinar. This webinar is the South African National Space Agency's webinar for the virtual edition of National Science Week 2021. My name is Mpho Tshisaphungo, and I'm the Communications Practitioner here at SANSA, the South African National Space Agency based in Hermanus. I will be introducing our presenters and panelists. The theme for this year's Science Week is making it possible through science. So for today's webinar, we will look at how blue skies research has led to practical applications relating to space weather. Our first presenter is the SANSA SARCHI Research Chair in Space Weather, Dr. Martin Snow. He is a solar physicist and he's pioneering this field in South Africa. Our second presenter is the SANSA Space Weather Practitioner, Mpho Tshisaphungo, who has been at the forefront of the South African Space Weather Center since its inception. After their presentation, our panel of experts will be available for a discussion and to answer any questions you might have around space weather. Our panelists are Dr. Rondani Ndangeni. She is a space weather researcher at SANSA, looking at the impact of space weather on aviation, with a focus on radiation exposure due to galactic cosmic rays and space weather storms. Our SANSA researcher, Dr. Chimangadzo Matamba, specializes on the effects of space weather on global navigation satellite systems, or GNSS, and the response of the ionosphere to space weather conditions. Dr. John Bosco Haboreloma is our third expert and will join us a bit later during the webinar. We encourage you to submit questions in the Q&A box during the presentation to encourage a fruitful discussion with the panel. And with that, I will now hand over to Dr. Snow for our first presentation. Over to you, Dr. Snow.
All right, thank you very much. So let me share my screen here. That's the right one. That looks like the right one. Okay, thank you for having me. So yes, I'm gonna talk a little bit about fundamental and applied research at SANSA, from blue skies to practical applications. And this is a sort of a combined talk. So I'll talk about the blue skies, and Mpho will talk about the applied research. So in the first part, I'll give you an example of a blue skies topic, the solar wind, and then kind of a highlights of some of the research, fundamental research that we're doing at SANSA. And then Mpho will take over and talk about the applied research. All right, so yes, what does blue skies research mean? It's a fundamental scientific research that, to me, it means learning about the basic nature of the world around us, even if there isn't some specific goal in mind, like this cat with the egg carton. Whereas applied research is often something that I might call engineering. It is how you solve the problems that the blue skies researchers create. So as an example, back in the 1930s, almost 100 years ago now, scientists sort of figured out, oh, the outer part of the sun is really hot. Most of the visible sun is about 6,000 degrees, and the very outer part, they figured out, was like 1,000,000 degrees. From looking at the sun during eclipses and taking the spectrum of it, the conditions out there had to be really, really, really hot. Another thing that people look at are comets, right? So you see these items in the sky that appear occasionally, have very pretty tails, lots of detailed structure in them, and you think, wow, what are those things? And really trying to understand what creates the tails of comets. That's, again, not anything that has a practical application here on Earth. But then when you start to combine the thoughts about those two things, you see that different comets coming in different directions and so on. They have very different kinds of tails. I don't know if you can see my cursor here, but most comets end up actually having two tails. One is made of dust that's reflected sunlight, so that's why it's kind of yellow, because it looks like sunlight. And then the blue stuff are ionized gases that get excited by the ultraviolet light from the sun, and then de-excite and produce this blue color. And so studying the tails of comets, you then realize that a comet tail always points away from the sun. So as comets come in and circle the sun, the angle of the tail changes to always point away from the sun. So now when you think back to that outer part of the sun is really hot, it's got to expand. I'm sorry. Let me fix my screen here. There we go. You probably missed out on the earlier part. Uh-oh. Zoom share. Is that better? Okay, so the comet tails are always pointed away from the sun. And remember before we thought that we saw the sun has this very hot, puffed out atmosphere. So combining those two things, you realize that the hot outer part of the sun must actually be flowing outwards as a wind. So so this is where the just a little blue skies research back in here, there we go, back in the late 1950s shows that we suddenly have a solar wind. Again, this is not something that in 1958 had a practical use. But then later on, not too long after that, we launched satellites into orbit, and they got up above the atmosphere and encountered these areas of high radiation. And as you move back a little farther, you realize that solar wind is impacting the magnetic field of the Earth. And you can see variations in the solar output here on the Earth all the time. And this has led from the fundamental research about like, oh wow, the sun is hot, to suddenly we can see the effects of the changing sun on our technological society. So we start to have communication satellites, GPS, and now we not only just like to think about the properties of the sun, but we need to start tracking them. So welcome to the present, where we not only know about the solar wind, but we actually track it on a daily basis and measure the density variations as they slide through. Pardon? Okay, hang on, sorry about this. Let me stop sharing here. There we go. So I want to share the right one. Sorry for the delay here. I can claim to be an amateur. All right, so now I'm going to share the screen. Going to share this one. All right, we think we finally solved the technical issues. Sorry about that. Okay, so where were we? We were here we went from just intellectual exercise of, wow, the sun is hot and it must have a wind blowing out of it, to we need to know where the wind is blowing, what its density is, and how is it going to impact the Earth? And we need to know this every day, right? So we went from just thinking about the sun to actually a practical use of needing to know forecasts of space weather. What's going to happen today? What's going to happen tomorrow? And Mpho will talk about that a lot more in the second half of the talk here. But as you can see, everybody is interested in watching this. So yes, we go from before. So here, every day, SANSA puts out a bulletin telling you what the upcoming solar conditions are going to be for the next day, the next 3 days, and so on, so that the power companies and aviation companies can plan for how to deal with that. So that was a big breakthrough, thinking about the sun, getting to a solar wind. And so what will be the next thing, right? So these are some topics that we study here at SANSA in sort of the blue skies mode of solar physics. How does the sun's spectrum vary over time? There's a little bit of practical applications to that once we figure it out, but thinking about why it changes. Another thing that we might do is measure atmospheric radiation propagation through the atmosphere. And the way you can do that is to launch high altitude balloons. Another topic that is studied here in plasma physics is understanding turbulence in the solar wind. So not just what does what are the conditions like for warning about how to protect your satellites, but also understanding the microphysics of how that all actually happens. Other things that we study here are what are known as black aurora. So the aurora are space weather events that you can see easily and are very beautiful. The black aurora is a special kind of aurora. We measure the total electron content in the atmosphere, measuring the reflectance from the atmosphere as a function of height and modeling how that changes over time. And of course, there are these things known as sprites. They occur over thunderstorms. So it's a very brief electrical output, lasts for like 50 milliseconds. So you can capture them on film, but it's hard to see them. But as you can see, they're very, very pretty and very interesting atmospheric events. Do we have a practical application for sprites yet? Perhaps not, but maybe in the future. Okay, so that's sort of a flavor of the sort of things that we call blue skies research. And now I'll switch the floor over to Mpho, who will talk a lot about the applied research here at SANSA. So just as soon as I get my screen sharing all fixed, then I'm no longer sharing.
Okay, thank you very much. Can you see my screen?
Yes, Mpho, we can see your screen. Thank you.
Okay. So thank you very much. I'm going to talk about the application of research that we do here at SANSA, and that is called space weather. So the content of my talk, I will speak about the space science research, and then I'll define what space weather is, and then a little bit about space weather monitoring and the impact it has on technology. And then I'll touch briefly on the careers in space science. So space science research, like you have seen from Martin's presentation, we have different areas of research here at SANSA. And so space science research in the practical application is known as space weather. So in the space weather, we are doing applied research or monitoring what is happening on the sun. And what space science research does, it helps us with the human capital development with transferable skills, and it improves our capabilities in space application and services. And it also inspires innovation through space knowledge and expertise. And it also provides us with the education and the inspiration of the youth. And we develop knowledge to address local economic situations through space science research. So the space weather, what we call the applied space science research, is that we are constantly monitoring what we call space weather, or the conditions between the sun and the earth. So we look at the sun, and then the solar wind, the magnetosphere, as well as the ionosphere and the thermosphere within the magnetosphere. So mostly this is our space laboratory. And to define space weather refers to the conditions on the sun and in the solar wind, magnetosphere, ionosphere, and the thermosphere that can influence the performance and reliability of our spaceborne and ground-based technological systems. So space weather has impact on our technologies. And when we talk about where in space, this is just to differentiate it from terrestrial weather. When we are talking about space weather, we are looking at a different altitude up in space. So we look at the sun and the conditions on the sun, the solar wind, and the magnetosphere. Ionosphere is a layer in the atmosphere, or the upper layer of the atmosphere. As you can see, it's indicated here. And then you can see it's different from terrestrial weather, because terrestrial weather happens down below this altitude. So the ionosphere starts from about 80 kilometers above the ground. And that's where most of these energetic particles from the sun, they get absorbed into this layer. And the reason why we monitor space weather, and this layer particularly, it's responsible for reflecting the radio wave signals. So you can do your high frequency communication, you can send your signal up in space and you reflect it within this layer, which is called the ionosphere. So when there is space weather event, the signal you are sending into space to do your communication can get attenuated within this layer or get absorbed within this layer. So it's important for us to monitor the space weather conditions, so that the people who are responsible for HF communications planning, they may make adequate backup solution in case of any space weather event. So on the space weather monitoring and forecasting, what we use is we have a lot of satellite data to look at the sun, just to monitor what is happening on the sun. So we are looking at real-time data or latest information that we get from different instruments. So you can see here on this image, we have different images of the sun. We look at what is happening on the sun. And then we also have ground-based instruments to look at the impact. So the impact of space weather, it has a regional impact. So that's why we need to have the ground-based instrumentation on a regional level, so that we can see the magnitude of impact. So here I just mentioned that we do space weather monitoring, forecasting, and predictions, and then we also disseminate this space weather information to our client via the public website, the email, SMS, and fax. And then we also do space weather analysis and verification of our forecast so that we can improve our forecasting in the future. So this is what space weather forecasting is all about in the overview, or just in general. So the space weather bulletin, we do publish space weather information on our website, and this is the link to our website. And then you can read about the current space weather conditions on a day-to-day basis. So the importance of space weather forecasting, the reason why we monitor space weather it's because it has impact on our different technologies. And then technologies also, they play an ever increasing role in our society because we are dependent on these technologies, such as the global navigation satellite systems, power grid, satellite communication, as well as high frequency communication. So here is just showing different systems that can be affected by space weather. Aviation is one, and also the human space exploration astronauts, they can also get radiation exposure due to space weather. And this is some of our technological systems that can be impacted by space weather. And the reason why we monitor space weather is because these systems, they get affected, and we need to plan if there's any severe space weather event coming our way to protect our technological systems. So in the fourth industrial revolution, our technology continues to play an ever increasing role in our society, and the potential for space weather storms from the sun to impact our daily lives is also growing. So we need to constantly monitor this technological infrastructure, such as power grid and GPS satellites used for communication and navigation, because they can be impacted by space weather. And then just to talk about the careers in space science, we have different space science careers here. And then to be able to follow the field or the area of space science at high schools, you need to follow the STEM careers, which is science, technology, engineering, and mathematics. And then here I've just put one few of these space science careers. We have space science researchers, is mostly the research that Dr. Martin has just presented in different areas. You can have, you can specialize on the sun or on the magnetosphere or ionosphere, depending on your area of expertise. And then we also have space weather forecasters. Then it's from the monitoring or the application side, where you monitor the space weather conditions in near real time and providing this information or service to the clients. And then we have satellite operations technicians, those who are monitoring and tracking the satellites. And then we have space science educators, remote sensing. And then here is just an example of our space science educator, where we do engage with our high school learners or primary learners, just to teach them about physics or space science things or space science field. So we do have a science advancement here at SANSA in Hermanus, where we do engage with these learners. And also we have the opportunity here at SANSA for the postgraduate bursaries, and you can find it on this website, and the application is open, and I think the deadline is in September for next year's bursary funding. And then we provide the bursary for postgraduate studies from honors, masters, and PhDs. So if you want to follow this career, it only starts from the postgraduate level. And I think that's done. Thank you very much.
Thank you very much, Dr. Snow and Dr. Tshisaphungo, for those lovely presentations. We would now like to see if there are any questions from our viewers about these presentations, any questions that you might have with regards to solar physics, the research being done here at the South African National Space Agency. We can also take questions on our new project, which is our 24/7 operational space weather center, which is being constructed as we speak outside of our building windows, which is a very exciting project and which would allow SANSA to monitor space weather on a 24/7 basis. So, okay, I see there's a question, where are you located? So thank you for that question. The South African National Space Agency's head office is in Pretoria. The space science program is being done from the facility in Hermanus, which is in the Western Cape. It's about an hour's drive away from Cape Town. And this is our magnetically clean environment, which we operate from, and where we do all kinds of research into the upper atmosphere and space weather. Okay. I think while we wait for more questions, I would like to ask, okay, here's another question. Has there been any change in the past 20 or more years with regards to the sun's activities, i.e. we are seeing more or less activity? So Dr. Snow, I think I will hand that one over to you.
Okay, so actually the solar activity level, has this periodic variation. It's about 11 years. Sometimes it's really big, and then other cycles are smaller. So actually the last solar cycle was about half as big as the one that happened in the year 2000. So it was a smaller cycle, and then the one that we are we're emerging from a minimum time and going into a new solar cycle, and indications are that will also be a fairly small cycle. So the sun has been less active over the last 20 years than it had been previously. So that's all we can say. We don't quite understand what makes one cycle bigger than the next, but that's something that is currently still a blue skies project of understanding that.
Thank you, Dr. Snow. I would also like to ask Dr. Tshisaphungo, have you seen the effect of the increase of solar activities from your applied perspective?
Like Dr. Snow has mentioned about the solar activity variations, the last solar activity or the last maximum activity that we observed was around 2014, 2014. And then around 2017, we were looking at the downside of the solar cycle. So the cycle or the sun's activity was going down a bit, and the last big event was in September 2017 that we observed here in the Space Weather Center. The other activities has been very weak or minor activities, not very big. So the cycle, it's approximately 11 years. So sometimes now we are in a period where the sun's activity is quiet.
Thank you for that. I'm going to also just pose that question to our panelists who are online, if you would like to add to that. Perhaps Dr. Nangeni can go first.
Thank you, Dalian. I think Dr. Snow and Dr. Tshisaphungo has covered everything with regard to that. So yeah, we are not seeing anything much activity. So hopefully when this cycle 25 picked up, we'll see much more exciting stuff happening on the sun.
Wonderful. Okay, with that in mind, let's move on to our next question here. Anonymous asks, Dr. Snow, does space weather have anything to do with extreme weather we are currently experiencing all over the world? And I think we've all followed the news stories of the flooding up in the Northern Hemisphere and some of the dark conditions in the Southern Hemisphere. That's a question I also get asked regularly, so please enlighten us.
All right, so yes, this is a question that comes up a lot of, how does space weather interact with terrestrial weather? That's what we sort of think of when we think of rain and lightning and so on. We call that terrestrial weather. So the sun, as we said, it has a cycle where it varies, on the scale of about a decade, 11 years. But over the last, we've been measuring it for centuries, and the sun has been very stable. Kind of, this periodic signal, but the amount of light change, the amount of energy we receive from the sun changes by like 0.1% over this solar cycle and just returns back to the same level. So that's been very constant for as long as we've been measuring it. The extreme weather obviously is a recent event, right? That, this is all started in the second half of the 20th century. And of course, it's very highly correlated with the change in the carbon dioxide levels in the atmosphere, as well as, other greenhouse gases and so on. So the short answer is no, that there haven't really been any changes in the sun that would account for changes in our climate patterns, that there are a lot of anthropogenic, things that are created by humans that have changed in that same time period. So I think the answer is pretty clear that it's not the sun, but the sun does provide the energy input to the atmosphere. So there's many feedback cycles of the solar energies absorbed in certain layers of the atmosphere, that then reflected back out into space or so on. So it's a complicated system, and understanding how all of those feedback processes is still ongoing scientific research. But when you look at changes in the sun versus changes in the atmosphere, nothing that the sun has done would explain the changes in terrestrial weather.
Thank you for that, Dr. Snow. Okay, are there anything that one of our panelists would like to add to that answer and to that discussion? Okay, good. Okay, so let's move on. We've got an interesting question here from Owen Bierkus. He asks, does SANSA have any satellites studying the sun, or do the agency just have ground-based instruments? I think I'm going to give this question firstly to Dr. Tshisaphungo.
Thank you very much, Dalian. Thank you for that question. So the satellite, we have a satellite program within the agency, and the office is in Pretoria, in head office. And there is a project called the Space Infrastructure Hub. And this is going to be a collaboration with the industries which are developing satellites. And they are working together to develop a satellite, South African-owned satellite. So there is a program, but it's still a small scale. and we are working together with the industries within South Africa to be able to achieve this. But we also have ground-based instrumentation in the Pretoria at Besu Space Operations. They do track satellites and monitor satellites. So mostly satellite engineers, they do fit in very well with space operations, which is in Hatbesu in Pretoria. Thank you.
Thank you very much for that, Doctor. And let's ask our panelists. Dr. Ndangeni, would you like to add anything to that?
Thank you, Dalian. Like Dr. Mpho has explained, we currently don't have any satellite in operation, but we do have a good coverage of the ground-based instrumentation that actually help us to determine the regional space weather impact also. So yeah, thank you.
Thank you very much for that. And Dr. Matamba, would you like to add anything about our coverage of our ground instrumentation?
Thank you, Dalian. I have nothing to add. Dr. Tshisaphungo and Dr. Ndaganemi has already clarified that we have a ground-based instrumentations that we can cover, that we look at to look at what is happening on the sun and also what is happening on our ionosphere. Thank you.
Thank you. And I see Owen Bekus is also said here, he's asked, who is responsible for predicting the space weather and sending alerts when there is solar activity? So I'll give that right over for Dr. Mpho, if you can quickly answer there. I think that's your field.
Yes, the people who are responsible for predicting space weather and sending out alerts is space weather forecasters here in the South African National Space Agency. We have a space weather center here in Hermanus, and that's where we do monitor these space weather conditions, and we do space weather prediction and forecasting and sending out alerts and warnings. Thank you.
Dr. Tshisaphungo, would you perhaps also just like to add something about the Space Weather Centre's ICAO designation?
Yes. Currently we are a space weather regional warning centers designated by ICAO, which is the International Civil Aviation Organization. And we are required to provide the space weather information to aviation industry by next year, November 2022. And currently we are building a new space weather center, which will be operating on a 24/7 basis, so that we are able to provide this service on a 24/7. Currently, we only monitor space weather during the day, working hours. But in the future, by next year, we will be starting to do this on a 24/7 basis. Thank you.
Thank you very much. That's very interesting. I think I don't see any more questions in the chat at the moment, but what I would like to do next is I would like to ask Dr. Matamba, who specializes in the effects of space weather on navigation systems, to perhaps just quickly take us through what are some of the dangers that space weather, what are the threats or that space weather has on our navigation systems.
Thank you, Dalian. The dangers on the impact on global navigation satellite systems like when we have solar storms, as you had when they were presenting. So when we have some coronal mass ejections from the sun, or when we have some solar flares from the sun, so it like interrupts with our instrumentations, and then it will might degrade our technological instruments that are placed on space. And also we can also see it on our measurements. So here on Earth, we use like a total electron content, as Dr. Martin has shown in one of his presentation slides. So like when there is an impact of space weather events, you will see that there might be a decrease or an increase in total electron content, like on the ionosphere. So like sometimes like you may lose, there might be a loss of log in the instrumentations, and then we might not get measurements, and then there might be some positioning errors on our result. Like when you use GPS, like for example, if you want to go somewhere, you might find that like your GPS is not showing you the right position where you want to end up. And then, so that could be due to the impact of space weather events, and then could be also due to some buildings that are around there. So it has like some interference with our instrumentations. So that's when we see like the impact on our GNSS instrumentations. So mostly like here at SANSA, we are modeling total electron content from the ionosphere, where we look every day, we check the behavior, how the ionosphere behaves like during solar events. So like when there is extreme solar events, you can see the impact. And then when there is no extreme solar event, you can still see like the stable ionosphere. So I think in a nutshell, that's what I can say about the GNSS navigation satellite system that we are currently studying at SANSA.
Thank you, Dr. Matamba, for that. That's very interesting. We've got another question here, which is also a very interesting one. How strong is the solar wind compared to wind on Earth? Dr. Snow, can you help us out with that one?
Yeah, that's actually a very interesting question. So here on Earth, the wind. I'm gonna try to convert miles to kilometers in my head, but we get strong winds that are maybe 150 kilometers per hour in a strong storm. Maybe in a hurricane it's a little more. So out in space, the solar wind is much faster. It goes, what we call the slow solar wind is 400 kilometers per second. And the fast solar wind is twice that. It's like 800 or 1,000 kilometers per second. So it's very fast, but it's also very low density, right? Out in space, there's not much, just a lot of emptiness, a lot of vacuum. So the particles are very far apart. And so, from the sun, they stream towards the Earth. And, in a normal gas here in the atmosphere, the particles are bouncing off each other many, many times per second. And they might go 1 million kilometers without ever bumping into another particle at all. So it's very fast, but very low density. And the particles are charged. So the electrons have been stripped off the atoms, and the electrons and protons are separate. So they can pull along the sun's magnetic field. And that's what really causes a lot of the space weather events, is the solar magnetic field that gets pulled along with the solar wind to crash into the Earth's magnetic field. And the two magnetic fields bump into each other, magnetic fields moving produce electric fields, producing changes in currents in the power grid, in the ground, and disrupting the ionization of the atmosphere and so on. So that's what causes all of those space weather events. But yeah, it's a great question of like, oh yeah, how does solar wind compare to terrestrial wind?
Thank you very much, Dr. Snow. Very interesting. Okay. David Oni asks, how does space weather affect satellites and specifically CubeSats? Who would like to take that one? Dr. Snow, you're up first.
Sure, I'll be happy to talk about that. Right. So, what do these space weather events do to satellites? So, if there's an eruption on the sun, often there is a release of X-rays, so very high energy photons, and they can damage spacecraft parts directly. They often, change the ionization in the atmosphere and so on. And then more importantly, the eruption might produce what we call a coronal mass ejection. So, so a blob of plasma and magnetic field from the sun that works its way out through the solar wind. So it may take a day or two to get to the Earth, but once it does, it crashes into the Earth, and those changing magnetic fields induce electric currents, and that can produce charges in the electronics on a spacecraft, cause upsets or damage to electrical components in the onboard computers. So that's one thing that can damage a satellite. There's not a lot you can do to prevent that from happening. Often, if there's a really extreme space weather event predicted, satellite operators may turn off a satellite, during a thunderstorm, right? You don't want a power surge to damage your television or whatever, so you may unplug it, or your computer, right? You have a power surge protector. Satellites try and build in protection like that, but you can't predict everything in space. So there's some steps you can take to protect a satellite if there's a coronal mass ejection on its way, but otherwise that's kind of the main thing, is the damage to the electronics through induced currents.
Thank you, Dr. Sloan. Just as a follow-up question there, is there any technology currently available to protect the satellites from solar flares and other extreme solar weather?
Right. So that's all part of satellite design. You want to make it as safe, as protected as possible. But one way to protect from X-rays and so on is to put lots of heavy shielding around it. But the heavier a spacecraft is, the more expensive it is to launch, and that gets into that engineering part of, okay, we can. There's some trade-off between making it bulletproof and making it affordable, right? So you can make something that will never fail, but it's way too expensive to ever launch. So that's a trade-off. Obviously, designing circuits for spaceflight is a little different than designing circuits for televisions, on the ground. So there's a lot of very specialized expertise that goes into designing parts that go on spacecraft. They need to be hardened against these radiation events, the X-rays, but also in the design of the components, you want to have a lot of redundancy so that if one part does fail, it doesn't damage it doesn't ruin the whole thing, right? So there's at least 2 sets of everything on a spacecraft to prevent a catastrophic loss of the entire satellite if a single part fails.
Thank you very much for that. Our next question comes from Owen Bierkes. He asks, does space weather have the same impact on all the other planets in our solar system besides the planet Earth?
Can I take that one?
Yes, please do.
So there's kind of two parts to that question. Do other planets experience space weather events? And the answer is definitely yes, right? That coronal mass ejections can hit other planets just as easily as they can hit the Earth. So certainly, you know, there's disruptions like that can happen there. You can see the Aurora, right? So the Aurora, the northern lights and the southern lights, the Aurora are something that visible that comes from the solar wind interacting with the magnetic field of the Earth. And you can see those on Saturn. So we have launched satellites, we humans have put satellites in orbit around other planets, and you can see the Aurora on Jupiter, Saturn, and so on. So yes, they do experience those sorts of events. But on the other hand, right, that the real impact of space weather is on our human technology, right? That we have satellites that need to communicate with the ground, we have electrical grids and so on. So as far as we can tell, the other planets do not yet have such technological societies living on them. So in that sense, no, they don't worry about space weather nearly as much as we do.
Thank you very much for that. How interesting. Okay. Another question here is, can meteorites and or other planets obstruct the monitoring of solar events? And what is the impact of space objects in the monitoring of solar events?
That sounds like a question for me, right?
Yes.
I don't want to hog time from the rest of the panel. So other planets do occasionally obstruct our view of the sun. You may have heard of things like solar eclipses, right, where the moon blocks out our view of the sun. But as you may also realize, that they're rare events and they don't last very long. And in fact, you know, when the moon blocks out the bright sun, we can see the corona of the sun that I talked about in the first slide, right, when I had the screens wrong. So we can see the outer part of the sun when you block out the bright part. So that can happen. And then the other bodies in the solar system, so Venus and Mercury, can get in between the Earth and the sun, but they take up a very tiny amount of space because, you know, Mercury is far away and very small, so it causes you know, a tiny fraction of a percent change in the, you know, it blocks out a little bit of the sun, and only for a short time. Meteorites are actually, you know, when you see a bright flash in the sky, that's actually from something about the size of a grain of sand. It's extremely tiny. If it's bigger, then it doesn't radiate as much as that. So yeah, the meteorites we see in the sky are really tiny. You know, I think astronomers might have another answer of you know, when they're trying to look at distant galaxies and so on, and then, you know, satellites, communication satellites pass through their field of view, or, you know, there are thousands and thousands of these new communication satellites in low Earth orbit that I think are really making the astronomers mad. So it's a problem to look at stars, but it's not such a problem to look at the sun.
Thank you very much for that, Dr. Snow. I see we have 6 minutes left on our webinar time, and we've answered wonderful questions. We've got two last questions. The one is, what is the average lifespan of a satellite, and what happens when a satellite fails? Is it left in space as space junk? And then following up on that is, there's a question on the ever big mystery of the Bermuda Triangle, and is it possible to tell what's happening there with our sophisticated technologies? So maybe we can wrap up our webinar with those last two questions, and then we can just, to finalize, just take a last round of comments from our panelists before we close off. So Dr. Snow, I'll hand back over to you.
Okay, so I can probably answer a little bit more about the lifespan of a satellite. So it possibly depends on the design of a satellite, right? So something tiny like a CubeSat that is made on a fairly low budget, it probably will only operate for 6 months or maybe a year or two before something fails on it. You know, a $1 billion communications satellite that you know, is broadcasting your satellite television or something, they plan on something like that lasting a lot longer, maybe 10 years or 20 years. I don't think that there are many satellites that really last a lot longer than that. You know, I think you hope that a satellite will last at least 5 years, and you know, depending on just how robust your design is, you know, it could last 10 or 20 years, but more than that is difficult. So then the question of, okay, well, what happens when your satellite fails? Some satellites, you know, have propulsion so that they can move and perhaps have a controlled re-entry into the atmosphere. But other satellites that don't have any ability to move around, they do kind of become junk, right? So so in low Earth orbit, you know, which is, you know, 600 kilometers above the surface or whatever, there is still a little bit of atmosphere. So over time, there's what we call satellite drag, right? Essentially, there's friction with the atmosphere that slows the satellite down a little bit, and it will eventually re-enter into the atmosphere and then suffer a lot of friction and probably burn up. But yeah, that may take decades. Usually there's some rule about when you launch a satellite, you need to have a plan for what happens at the end of its life. And you know, you can't just pollute the orbital space with too much junk if you can avoid it. But so yeah, that's kind of the short answer is, yeah, often it becomes junk, but it doesn't stay junk forever. The sun, you know, this is where the sun can help, right? An active sun puffs up the atmosphere a little bit more and produces more drag on the satellites so that they re-enter a little quicker. All right, and then I'm not sure that I can answer anything about the Bermuda Triangle. As a child, I remember hearing about it a whole lot, but I don't think that there's any physical model of what might be represented by the Bermuda Triangle. So it's difficult for physics to answer that. So I'll leave that one as something to just ponder.
So it remains a mystery. Thank you, Dr. Snow. Okay, so I think let's start to wrap things up. Before we go to the rest of the panelists, I would just like to bring our participants' attention to the following 2 things that I've posted in the chat of this webinar. The first thing is the South African National Space Agency's virtual exhibition for Science Week on Vimeo. I've shared the link, so please go and have a look. We had lots of fun making that virtual exhibition. We filmed it here at SANSA, so please feel free to go and have a look and share with anyone. We have also shared the HSRC. It's a questionnaire that they have asked us to share with you. So please go ahead, click through, answer the questions. It will really help us to get a good understanding of who our audiences are and how we can better present virtual exhibitions in the future. Okay, so let's go just do the rounds, and let's start with Dr. Matamba. Any closing remarks from your side? Dr. Matamba, you're on mute.
Thank you very much for the opportunity, and then also to attend this wonderful presentation by Dr. Snow and Dr. Mpho Tshisaphungo.
Okay, is that, thank you, Dr. Matamba. Wonderful. Dr. Ndangeni, any last remarks from your side?
I just want to say thank you to all the attendees, and then I hope they've learned something about space weather, and then they are interested because we are looking for the new generation of the space scientists, and we are looking to them, and they should apply for the bursary opportunities that are out there. Thank you.
Indeed, thank you very much for that reminder, Doctor. Yes, we do really encourage everyone to have a look at those opportunities that are available, and we promise you SANSA is a wonderful place to further your studies and learn more about space weather and to work as well. Dr. Where are we now? Tshisaphungo, any closing remarks from your side?
Okay. Thank you very much, Dalian, and thank you to the participants. I would just like to thank you, everyone who attended, and just want to emphasize the lookout for the careers in space science here at SANSA and the opportunities that we have, bursary-wise or just the jobs which are available. And also just to encourage the learners that great works are performed not by strength, but by perseverance. Thank you very much.
Thank you very much for those encouraging words. Dr. Snow, any inspiring words from your side?
Well, I don't know if I have inspiring words, but I'll echo what everybody else has said of the, we invite students at all levels to learn more about space and space science, possibly through a bursary that SANSA can offer to help your studies and to become a more solar physics pointed group here. So I welcome students to want to come work with me or work on any of those other projects that I talked about in the Blue Skies section with some of the other scientists here at SANSA.
Wonderful, thank you. And I see we just got a comment from Shadrach as well saying, thank you all. It was a very informative session and enjoyed every bit of it. Thank you for that wonderful feedback, Shadrach. We also enjoyed sharing the work that we do here at SANSA. If you have any more questions that we haven't addressed during this session, please feel free to contact us. Our contact information is on our website, sansa.org.za. Please go over and have a look. We're open to communications and to any questions. And I would just also very much like to thank our partners in this webinar, the DSI, Science Week, the NRF, and SASTA, for making this webinar a possibility and allowing us this platform to engage with people on the very interesting work that we do. And with that, we would like to close this webinar. Have a wonderful day, everyone. Thank you.